Hello there, everybody.
Technically, the bell
and
rings
welcome
now.
to the second episode of Science with Sijal. I'm your host, Sijal, and on today's episode, we're going to be talking about thin film interference. To help me explain further, I have two special guests here with me today. Put your hands together to help me welcome Professors Austin Kofed and Cynthia Jarvis.
Have you ever looked at the back of a CD and it looks like there's a rainbow reflecting off of it? That's an example of thin film interference. Thin film interference consists of two important factors, a thin film and light interference. Here's how it works. Light comes through air and hits the thin film. In the case, this thin film is oil. Part of that light gets reflected back into the air, but the rest is refracted into the oil. Shortly after, the refracted beam meets the third medium, in this case water, and the same thing happens. Some of the light is reflected back into the oil while the rest is refracted into the water. The reflected beams are what our eyes eventually see, but now there are two of them, one reflected off of the oil and the other off of the water, and they interfere with each other. All we have to do is now figure out whether the interference is constructive or destructive. Firstly, we have to see if the two rays are pi shifted or not. A light ray is shifted by pi radians, or exactly half of a wavelength, if it refracts from low to high indexes of reflection. The importance of this will become clear later. Now we have to find the time that the second wave is offset from the first. Knowing thickness of the film and the index of refraction, we can calculate this. Firstly, the speed of light in a vacuum can be divided by the index of refraction in oil to find the speed of light in the oil. Then the thickness of the film, essentially the distance the second wave has to travel, by the speed of light, the time it takes. However, the light has to travel across the film twice, once towards the water and the second time after it was reflected, so the time needs to be multiplied by 2. Finally, using the wavelength of the light, we can determine if the waves interfere constructively or destructively. However, if there is a pi shift, as mentioned before, then constructive interference occurs if they meet at half wavelengths, not full. This process can be simplified using the following formulas, where m is any integer. So here's an example question. The diagram below shows one way of light of a wavelength lambda and is reflected off the top surface of a soapy film. A. On the diagram above, draw the path followed by the ray after it enters the soap film. Well, we know that air has an index of refraction of 1. Soapy film has an index of refraction of, well, likely greater than 1. And air has also an index of refraction of 1. Therefore, as the ray right here, refracts into the soapy film, it will come at a lower angle, right here. This theta will be lower than this one. So when we draw the ray, it will be something like this. Then as the ray rebounds off of this, reflects off of this soap film on this side, it will bounce back at the same angle right here. So this angle is also equal to theta 1. And then it will refract back into the air right here. Now these two waves are what your eyes see, and they're actually parallel to each other. And the interference between the two is what causes the thin film interference. Okay, B. On the diagram above, identify with the letter X any points where there is a pi phase change. Explain your choice. So a pi change occurs anytime a ray goes from a low index of refraction to a high index of refraction. And in this case, that happens right here as the light wave shifts from an index of refraction of 1 to greater than 1. And therefore here is where we'd have a pi phase.